Hi, everybody. My name is Iqbal Khan. I don't know if I'll need the mic or not because I like to walk around, but I guess I'll stand here most of the time. Okay. Today's topic is scaling .NET applications with distributed caching. I did the introduction already, but I wanted to just kind of do it in front of, by keeping our website. We basically have two products that might be of interest. One is NCache, which I talked about already. The other is a NoSQL document database. It's a full JSON document database called NosDB. It's like a MongoDB, but native .NET. It is, both of these are open source products. We do have enterprise editions, so both. I just want you to keep both of these in mind. Okay. So I prefer to have a more interactive discussion. So if you guys have any questions, please raise your hand so we can talk about it right at that time instead of waiting until the end. Okay, let's get started. Let's get a few definitions out of the way. I hope I have started the recording. Yes, I have. Okay. So let's get a few definitions out of the way. First of all, what is scalability? Scalability is not performance. If you have 5 users of your application and the response time is super fast, your application is not necessarily scalable unless you can have the same performance with 5,000 users or 50,000 users or 500,000 users. So scalability is high performance under peak loads, under a lot of load. Linear scalability is more of a deployment definition. If you have an application architecture that allows you to scale the transaction capacity in a linear fashion by adding more servers, then you achieve linear scalability. That means if you had 5,000 users with 4 servers, 5,000 with 5 servers, and you added a 6th server, your capacity will now be 6,000 supposedly, and then you can add more servers as you need more and more load. In all of this, we're talking about transaction capacity. How much activity can your application do? How many user requests can it process? How many data processing transactions it can do? So we want to definitely achieve linear scalability. Non-linear scalability is where, even if your application, if you add more servers, after a certain point, you're not able to speed up or increase more capacity. You definitely do not want to be in a non-linear scalability architecture. Which applications need scalability? These are web applications, ASP.NET, ASP.NET Core now, web services, backend for IoT, which is usually, again, web services, big data processing. Big data processing is not that popular in .NET, but it could be. But at least any big data processing application needs to scale. It needs to be able to handle a lot of transactions in a short amount of time. And any other server applications. You might be a bank that has millions of customers, and you have to process maybe change of address, or maybe they're doing transfer some funds, whatever. They want to issue a new card, and you need to process that within a certain amount of time for compliance purposes and also for your SLA or your customer satisfaction purposes. So as you get more and more of these transactions, the time does not increase. So you need to be able to add more servers, but if your application is not scalable, adding more servers, as we just said, will not help at all. So if you have any of these applications, then you've come to the right talk here. So where is the scalability problem? It is definitely not in the application tier. Most web applications, web services, other even server applications here, the application tier is usually fairly scalable. It's the data storage and when I use the word data storage, I mean relational databases or mainframe data. That is the bottleneck. So that is the tier that cannot scale. You can add data, but you cannot add a lot of transaction capacity. And no SQL database is not always the answer. Now, no SQL databases became popular because one of the reasons was that they were solving scalability problems. They solved scalability problems not only for transaction but also for data. If you wanted to store huge amounts of data, you could, NoSQL database was the more appropriate place to store it. And definitely transaction, you could add more and more servers, and the NoSQL database is never a bottleneck. So why is that not always the answer? Even though we have a NoSQL database product of our own, the reason is because a NoSQL database requires you to move data from your relational database into a NoSQL database. So if you want to continue using SQL Server or Oracle or MySQL, then NoSQL database is not going to be of any help. Now, you may not be able to move that data for a variety of both technical and business reasons. So the reality is that you have to continue to work with relational databases. Now, NoSQL databases are becoming popular not as a replacement of all relational data. So the most common use cases are where you have a hybrid of both relational databases and NoSQL databases. So relational databases, your legacy mainframe data is here to stay. So whatever scalability problem you have to solve with these technologies in your architecture. And that is where a distributed cache really comes in as a very useful technology. It allows you to continue to work with your relational databases. You can still have a NoSQL database, but some or a lot of your data will continue to reside in relational database or legacy data. And you just put a caching tier in between the application tier and the data tier. So you know that the application tier is usually a load balanced tier. So if this were a web application tier, you would be able to have a load balancer up here and add more servers here as you need more and more traffic. So if you have more user traffic, just add more web servers. The same thing goes with web services. If you have more web method calls, just add more servers. But you cannot do that here, right? But what you can do is put a caching tier in between with a minimum of 2 cache servers. These are inexpensive servers. The keyword here is inexpensive. These are not high-end database servers. These are typical web server type of configuration. Dual CPU, like an 8-core box, usually just lots of memory because it's an in-memory store. A distributed cache essentially builds a cluster of multiple servers. As I said, 2 or more, 2 for redundancy purposes, and more because you need to scale. So as you need to scale, you put more here. So a distributed cache, let's say like NCache, will build a TCP-based cluster. And it's a peer-to-peer cluster, so you can add more servers as you need to increase capacity. Your application will never, and about 80% of the time, you will be able to get all your data from the caching tier. 20 to 30% of the time, you have to still go to the database, because all the updates still have to be made to the database. That's your master store. All the updates will always go to the database. The reads, of course, will go to the caching tier. The first time you'll get it from the database, and then it'll go to the caching tier. So by having this caching tier in between, suddenly you no longer have those scalability bottlenecks that you would if you did not have this. So caching tier, which on the Java side is called in-memory data grid. On the .NET side, it's called a distributed cache. Another word for this is an in-memory NoSQL key value store. So there are different ways to call this. In fact, if you watch Martin Fowler's talk on NoSQL, he talks about the key value stores. So NCache itself is actually a NoSQL key value store, but it's an in-memory store. So having a distributed cache as a layer in between makes sure that your application never becomes a bottleneck. And you can continue to use NoSQL for other purposes that I'm not going to go into. The goal of my talk up until now is to convince you that as a best practice, you must incorporate a distributed cache in your application architecture. You must design your application to have a distributed cache in mind. And then once you do that, especially if you have a server application that needs to be able to scale, it may not need to scale right now. It may need to scale down the road, but you need to architect it today for scalability. The really painful thing about not being able to scale is that you face problems when your business is really doing well. You're getting a lot of activity. Think about, let's say if you're an airline and you just did a marketing promotion for for let's say Hawaii or maybe to Europe, and over the weekend everybody's going to log into your website to do flight search and they'll buy tickets. So your website traffic has suddenly quadrupled, and if your infrastructure was not able to handle that, at the minimum your response time is going to shoot up. Your average click will come back in 30 seconds or 45 seconds or maybe even more. And in the worst case, your website may even crash. I was at Expedia the other day, just about last week, I think, and it crashed. And it was down for some time. So anyway, if something like that happens, you lose a lot of business. You lose hundreds of thousands of dollars per hour when something like that happens. And you cannot buy your way out of that problem. Unless you've architected the application to use this technique, this technology, you cannot at that time say, okay, well, let me just put some extra database servers. The problem is that relational databases by design cannot be, they're not distributed. So you cannot have 5 or 10 database servers. You can have 1, maybe 2. Some people have maybe slightly more than that, but they really don't scale. They're fast, but they're not scalable. So make sure that if there's one thing that you get out of this talk is that you must have a distributed cache as part of your application architecture. So now that let's say we are in agreement that you guys need to use a distributed cache, as .NET developers, what do you need to do? I mean, how do you use it? Where do you use it? What are the use cases? What type of data can you put in it? So there are 3 high-level use cases. Number 1 is the application data caching. This is the same case that I was talking about, where you have a database, which is called the application database, and you cache data, so you don't have to go to the database. 80% of the time you get your data from the caching tier. So database is much lighter now, so it can perform even the updates much faster. So that's the first use case. Now, one thing to keep in mind, and we'll talk about this in the subsequent slides, is that in the application data caching, the data exists in 2 places. One is in the database, one is in the cache. When a data exists in 2 places like this, what's the first concern that comes to mind? What could go wrong? Stale data, or they could go out of sync. So the cache could have an older copy. So I could withdraw $1 million from the same bank account twice, I guess. Of course, you don't want to do that. So whatever you do, if a cache cannot handle the staleness problem, then you're forced to cache read-only data. In fact, if you ask an average person who knows what caching is, just as in a brief or has really a high-level view of the cache, the knee-jerk reaction is, what should you cache? Is, well, read-only data. I'm just going to cache my lookup tables that are not going to change at all. Well, the read-only data is only 10-20% of your data. What about 80 to 90%? So if you really want to scale, you need to cache that 80 to 90% of that data Otherwise, the cache is really not achieving the results that you want it to achieve. So a good cache must make sure that the cache is synchronized with the database. So it is never stale. Second use case is ASP.NET applications, which is in addition. I mean, ASP.NET applications would be doing application data caching, but in addition to that, there's some ASP.NET specific data that you could be caching. The first is session state, which almost everybody knows what that is. Session state, by default, Microsoft gives you the option of storing it either in proc or SQL Server, and both of them have scalability problems. In fact, SQL even has performance problems because sessions are stored as blobs, and relational databases were not designed for blob storage. Whereas a distributed cache is a key value store. So what is the value? It's a blob. It's a byte stream. So it is ideal for storage of this kind. So session state storage is ideal for storage in a distributed cache. The next is the view state. If you are in the old pre-MVC framework of ASP.NET, you probably have view state. And view state, for those of you who don't know what view state is, it's an encrypted string that is sent by the web server to the browser, only to come back at a postback. So it makes that long trip just to come back again. And this view state could be hundreds of kilobytes. And multiply that by millions of transactions that your website or your web application has to support. You're consuming a lot of bandwidth, which is not free, by the way. Bandwidth costs money. So your infrastructure cost has gone up. Second, your response time is slower. Because you have to send a few hundred kilobytes of extra data. It goes and it comes back. So it's a heavier payload. It would be a lot easier if you just sent a small key and cached the view state on the server end. So when it came back, that key would come back and you would just fetch it from the cache on the server end. So view state is another very useful use case. The third is ASP.NET Output Cache, which is a Microsoft ASP.NET framework that allows you to cache the page output if the page is not changing on the next execution. So you don't have to execute the page. And even there, instead of storing that in a standalone cache, if you have a load balanced web farm, then you should store it in a distributed cache so that the first time you store it, then everybody else will automatically use it. The ASP.NET specific caching use case say that the cache should become your master store. So you should no longer store this data anywhere else. It should be stored in the cache. And a cache is an in-memory store. And when you have an in-memory master store, what's the biggest concern that comes to mind?
Hope your machine never crashes.
Yeah, so hope your machine never crashes because you'll lose data. So you don't want to be that airline where a customer spent 30 minutes or more searching for their perfect combination of flights, and as soon as they were about to hit submit, their session was lost because the web server or the cache server crashed. So a good distributed cache must provide reliability. There must not be data loss. And the best way to provide reliability in an in-memory store is through replication, to have more than one copy of that data across multiple servers. So a good distributed cache must provide replication, and that replication must be fast. The third use case is runtime data sharing through events. A lot of people don't know this, although now it's starting to become more and more known, is that a distributed cache is a very powerful and very simple way of sharing data across multiple instances of your application or even across multiple applications. When do you need to share data? Usually when there's like a workflow type of a thing, where somebody produces something and somebody else is waiting for that change to occur. There could either be a complete pub-sub model where one producer produces and publishes it, and there are a bunch of subscribers that get notified. That's one model. There's also just simple events. An application could say, notify me when this key changes or when this item changes. Or there could be this thing called continuous query, which is like a SQL statement, It says something like select customers where customer.city equals Chicago. So any customer object with this criteria, if it's added, updated, or deleted from the cache, notify me. So it's a much more sophisticated monitoring of data changes into the cache. So there are different ways that applications can be notified.
So where would you put this if you're using reactive messaging and you've got a messaging queue that is able to supervise the speed and quantity of the messages coming in? Where would you put your cache in relation to the message?
Yeah. So essentially what this is saying is that for this use case, you're actually using a cache instead of a message queue. A message queue, it has its own purposes, and a cache does not provide all the features of a message queue. But a lot of the applications don't need all the message queue features, but these applications have high scalability requirements. So if you have this environment where you have, let's say, 10 or 15 or 20 servers constantly doing activity, a distributed cache scales much more so than a message queue would, because you can add more and more servers to the cluster, which a message queue was not designed for scalability. It was designed more for delivery, to ensure that a delivery actually happens. It has more features. So MSMQ has a lot more features that any distributed cache will have. RabbitMQ also has more features. So if you need all those extra features, then yes, go through it. But a lot of most of the applications don't need all the features. And if the features that you need are being met through a distributed cache, use that, because you have it in part of your infrastructure anyway. And it's a much faster and more scalable alternative.
Would you ever use both just to make sure you know what's in the queue at any given time to keep the state of the queue?
You could. I mean, you could do some of the messages through the message queue, some through the cache. I would probably not put the same message through both, because it just there's no benefit. But I think whatever you put through the cache, it's going to be much more scalable. So if you are doing a lot of activities, if you're doing a lot of transactions, and those transactions involve coordination, this runtime data sharing, event-driven sharing, then use a distributed cache. It's a much better way to do it. Good question. Runtime data sharing is also something where most of the time the data only exists in the cache, although it also exists in a different form in the database. Maybe it exists in some raw form in the database, and you produced it and you kept it in a more in a different form in the cache. So you still don't want to lose this data. So the second and the third use case require the cache to provide replication. The first use case can live without replication, but even there, what we've seen is that our customers, they say, well, if I don't replicate and a server goes down, I'm going to lose 1/n of the cache. And I will be able to rebuild that cache from the database, but it's going to have a performance hit on my database, because now I have to go to the database to load all that data. So all those future transactions which need that data will be slower until that data is cached also. So why not just replicate even there? So in all three cases, replication is used, and in the first case, there's other features are used, which are to make sure that the cache is kept synchronized with the database. Any questions up until now?
Probably for the data sharing, how do you handle the events? Like the data has changed in the cache. How do you observe that event?
So basically, what happens is that your application, and I'll show you the source code also, your application actually registers itself with the cache and provides a callback. So your callback gets called. Okay, let me first, before I go into more features detail, let me show you what a cache looks like. I'm going to, of course, use NCache as the example. I have created a bunch of VMs in Azure. So NCache you can use either on-prem or in Azure. So I have two, Demo 1 and Demo 2 are my two cache server VMs, and Demo Client is my application server box. So I'm logged into my Demo Client here. I'm going to go ahead and use this tool called NCache Manager right here. And this tool you can use from a single location. And you can come here and say, create a new clustered cache. So think of this cache as an in-memory database. So just like in a SQL Server, you first create a database and then you work with that database in your application. It works exactly the same way here. So you create a cache. All caches, in case of NCache, are named. I will pick a caching topology. I'll come back to what a caching topology is at the end of this, but I'm just going to pick a partition replica topology. I'm going to pick asynchronous replication. I'll also come to this. I will pick my first cache server, which is demo 1. I'll pick my second cache server. So now I have a 2-server. I'm going to build a 2-server cluster. It's going to use this as the default TCP port. I'll just take the default. It wants me to specify how much memory I want to allocate for caching in each server. So I'm just specifying 1 gig. In your case, actually, a typical configuration that we've seen is a cache server is 16 to 32 gig of memory. Each cache server has about 16 to 32 gig of memory. Less than 16, we recommend that because memory is so cheap, we say keep at least 16 gig. As I showed, when you build a cluster, it pools the memory of all the boxes. So here, if I specify 1 gig, that 1 gig is for the partition and 1 gig will be used for the replica. Let me just quickly show you what that is from a picture perspective, just so that I'll come back to this. So let's say if I had a 2-node cluster, server 1, server 2. Every server has 1 partition and has 1 replica of another server partition. So if I specify 1 gig as the memory, I'm specifying the size of the partition here. So the total memory consumed will be 2 gig. You should leave about 2.5 gig for the OS and other processes. Basically, what you don't want to do is do paging. You don't want to create the cache size which is more than the memory, because what's going to happen is all of this is virtual memory, right? So as soon as the actual memory consumption goes beyond the RAM available, Windows will start to use virtual memory, and virtual memory does paging, which has a lot of performance degradation. So the whole purpose of a cache dies if you're not able to work within the actual memory RAM that you have. If you go beyond what that is, if you don't do the proper capacity planning and the cache size that you specify is more than the actual memory, when you hit that upper end, you'll see that the cache will slow down because it's doing paging now. So you don't want to do paging. So I'm just going to pick the cache, and then so I'm going to pick an eviction policy. Eviction policy is, it says when the cache is full, when it has used all that memory, what should it do? It's an in-memory cache, right? So it can do one of two things. One, it can reject any more new additions of data, or second, it can evict some of the existing data. By default, you want to evict data in case of application data caching. In case of application data caching, it's okay to evict, because you can always get that data again from the database. In case of sessions, it is not okay to evict, because that session may be active. So in NCache, there are two terminologies that we use. One is called eviction. Eviction is the forced removal from the cache because there's no space left. And the other is called expiration, and I'll come to expiration in a bit. You want to expire the sessions and not evict them. I'll come to that in a bit. So I'm going to create, so I've got a 2-node cache configuration. Now I'm going to come here and create and add a client. Client is my application server box. So as you can see, in case of NCache, you can do it all from a single Explorer style interface. So it takes that long, just to create a 2-node or 3-node or 4-node cache cluster. And the way this works is, let's say you created a 2-node cache cluster, and now it has just started. Okay, so I'm going to view some perf counters here. I'm going to also do monitor cluster. NCache has this really nice dashboard style monitoring tool. Oops, here. And I'm going to come here and I will say stress test. So I'm going to actually run a stress test. NCache gives you a stress test tool that lets you very quickly, without any programming, test activities against your cache. So you can simulate what the application will do, your application will do. How many reads, how many writes, what's the average object size, so that you can see how the cache will be performing in order. Right now I'm doing about 500 requests per second from each box, about 500 to 700. Let me go ahead and add one more stress test tool. You'll see that capacity will double, see, about 1300 each. Let me add one more stress test tool. So this is basically like your application sending more transactions to the cache. And suddenly now I've got 2,600 per box. So what happens? You keep adding more and more transactions, right? At some stage, this is going to become a bottleneck. So just like a database, these 2-node cluster will become a bottleneck. And you'll see that the performance will start to slow down. So, but unlike a database, you can come here and say add a node. And you can add a third cache server at runtime. And suddenly, your capacity has increased. And then you'll max out the third one, then you add a fourth one. And so that's how you grow, just like you would do it with an application tier. So the ability to add or remove these at runtime is the real key power of a good distributed cache like NCache. So I'm just going to go ahead and stop this. Okay. So now that we know what a cache looks like, in case of NCache, all caches are named. Let's go into these use cases. So I'm going to actually go to this one first, and I'll come to this. The nice thing about the ASP.NET specific caching, if you want to benefit from it, is that there's no programming needed. Everything you do is just a config change. So for sessions, what do you do? Let's say I have this sample here. So let's say I have this ASP.NET application. I just need to open the web.config. I need to add this assembly line here. This is the NCache. So this NCache.SessionStoreProvider has implemented the ASP.NET Sessions Store Provider interface. Because ASP.NET Framework has an interface where third-party storage providers can plug in. So by implementing that, NCache becomes a session store provider. You just have to come here and configure it. So you make that change, and the second change you make is you make sure the mode is custom. You make sure your timeout is what you want your session timeout to be. And in case of NCache, you just copy that line, and within that line, you just need to specify a name of a cache. Just like you need to have a connection string for a database, here you just need to have a name of a cache. And from this name, what happens? So let's say I was on this is my application server box. So when I created this cache and I added this as a client, I'm on this box right now. So on this box, if I come within program files NCache config, there's this client.ncconf file. So it creates an entry called demo cache. So that is done automatically for you, and that's how you can use a cache name to go and talk to the cache cluster. So your application specifies the cache name, NCache client API goes into this file, picks up any one server that it can talk to. Once it connects to that server, everything is dynamic after that point, and I'll go into that detail afterwards. But that is how you are able to specify just a cache name here. So for ASP.NET Session State, the process is very simple. You install NCache on, let's say, 2 or more cache servers. You install NCache client portion on your application box right here. you create the cache that we just did, and you go and modify the web.config. Because whatever cache you created here, you added these boxes as the client boxes. And by adding them, NCache Manager updated the client.config file in it. And then you go to those boxes and modify web.config the way I just showed you. That's all. This whole process takes less than half an hour. If you had, of course, the boxes. That's why we always tell customers, if you want to use a distributed cache, start from sessions, because that's the easiest way to get things started. There's no programming. That means there's no proper QA that you have to do. You just have to do some sanity testing. And you need to do some benchmarking and stuff to make sure that this cache performs in your environment. Because sometimes you've configured the cache improperly and it doesn't perform, and our customers will call and say, well, NCache was supposed to be fast, it's really slow. And then we see maybe they've done something wrong in configuration, and that's how so ASP.NET session state, very easy to do. If you're doing view state, very easy to do. The problem with ASP.NET, with the application data caching is, with ASP.NET Core now, there's a distributed cache concept as part of the framework. NCache has also implemented that. So but even there, you have to make calls to the distributed cache API standard. But there's always programming involved. However, if you're using EF core, EF7, then you can use NCache as a plug-in L2 cache, and there's no programming needed on your part. NCache allows you to do, so if you don't want to do any programming and you still want to do application data caching, then you have to be using one of the OR mapping engines. So there are two that we support. One is EF, one is NHibernate. So if you're doing any of those two engines, then we can plug in. If you're not doing any of those engines, then you have to make API calls. And actually, API calls is not a bad idea. It's not a very complicated task because you gain a lot of features, and I'll go over the benefits of those. So any questions on ASP.NET specific uses?
When you talk about tying into the ORMs, are you really talking about cache invalidation? When you're updating a database and you want the cache to update as well, keeping it sync, are you managing that synchronization and invalidation of your cache?
Yeah, so in case of an ORM is the one that has built the strategy for, so it has a cache interface that we have to implement, and it makes the calls to the interface. So when, let's say in case of EF, when you want to get a collection of entity objects, EF will make what, in case of NHibernate, let me just go into, because they've supported this for a long time. In case of NHibernate, when you want to get a collection back, NHibernate will check the cache first. It'll make the cache interface call, and if the cache says, I don't have this data, then they'll go and get it from the database, and they'll tell the cache to cache it. So the next time, again, they'll ask the cache first. So because they've implemented that much behavior, we can plug in very easily. But if there's no ORM in your application architecture, then you have to make those calls yourself. Because an NCache or a cache like this is only a recipient of your calls. Unless you make calls and tell it to give you something, and if it doesn't have it, it's going to say, I don't have it. Or there's some other features where it can go and get the data from the database too. But yes. Yeah. So let's dive into the meat of this, which is application data caching, where you have to do programming to actually do it. So how do you do it? So the first thing you need to see is, what does a cache API looks like? It looks very simple. This is an ASP.NET cache-like API. NCache, it's an NCache API, but it looks very much like ASP.NET cache object. If you look at it, so there's this is NCache specific. You connect with the cache, you get a cache handle. You do a cache.get contains. You do add, insert, remove, and they all have an async version. What does an async version mean? It means that you're telling the cache, well, give me the control back and please go and complete the operation for me. Because I don't want to wait for the cache to be updated, because I trust that it's going to be updated. Because unlike a relational database, which can refuse your updates based on check constraints, referential integrity constraints, Distributed cache does not refuse your updates. The only time it's going to fail the updates is when some system issues happen. There's not enough memory or some other things happen. So there's no application logic issue for refusing. So it's safe to go and update and just do an async update. Of course, if the data is very sensitive, then you don't want to do it async. So this is what a cache looks like. Let me actually show you. So I'm going to go ahead and this. So I've got this sample called basic up. Oops, not this one. So I've got this very small console application that is using NCache. So it's just it's like a hello world equivalent of this. The first thing that you need is 2 assemblies of NCache. So ncache.runtime, ncache.web. So ncache.web is the main API. Then you need the namespace here. And then at the beginning of the application, you need to connect to the cache and get a cache handle. If you had an ASP.NET application, you would be doing this in a global.asax, and the application start or init. Once you get the cache handle, you create your object and you do a cache.add. You specify key. This key is not very good. It should be much more specific. Here's the actual value, which is the object. This object actually gets serialized and sent to the cache and stored. So when you make that call, for example, in case of NCache, so let's say I'm just going to again skip some pages. Let's say if I had a 2-node cluster, you made that call from this box. It's going to go to, let's say, partition 1 because somehow that key belongs to partition 1. It figures that out. It will go and ask partition 1 to go and update itself. And that's, let's say, item number 2. And then partition 1 will talk to its replica, which is on a different server, in an asynchronous fashion, unless you wanted that synchronous replication that we had at the time of the cache creation. If you wanted a synchronous replication, then the client will wait until the replication also completes. You will do synchronous replication where the data is very sensitive. Let's say it's a financial data. You want to make sure it's kept in 2 places. Otherwise, most data you will just do an eventual update. That's the model that you have to get comfortable with. So that one cache.add would add the data here, and it would get replicated here. So there's a lot that gets done under the covers. So very simple API. Okay, so let's now come to the first concern that we had showed when you have application data caching. What is the first concern? The first concern was that the cache must be fresh. If the cache is not going to be fresh, you will only cache read-only data, which defeats the whole purpose. So what are the different techniques for keeping the cache fresh? Number 1 is expiration, which pretty much everybody has. All the caches, Redis also has it, NCache of course has it. What is expiration? Expiration is something that so there are 2 types. One is called absolute expiration, the other is sliding. Absolute expiration is what matters here. Absolute expiration is where you're telling the cache, I feel comfortable caching this data only for this long. Let's say 5 minutes. After 5 minutes, please remove this. Please expire this from the cache. Because I am afraid if you don't expire this, the data will go stale. Somebody's going to change it in the database. So here's how you do it. So that same call that you had, cache.add, here's the key value, and there's a calendar in this case. In case of NCache, you get to specify an absolute expiration, which is 1 minute, let's say. So you're saying just now plus 1 minute. Okay. So by just saying that, you've just told the cache, and the cache will now create a monitoring mechanism within its own store. It will actually, again, I'll go back to that picture. It will monitor this in the partition, and it'll also monitor this in the replica. So let's say after 1 minute, the cache has its own intervals after which it says, okay, now I need to go and clean some expirations. It's going to go ahead and remove that item, and once that item is removed, it's going to also be removed from the replica. All of that's done automatically for you. So you don't have to do that bookkeeping. And by doing that, the cache is allowing you to keep data fresh through expirations. So the sliding expiration, on the other hand, has a totally different purpose. It is more of a cleanup job. So you use the sliding expiration of saying, expire this if nobody touches this object for this long. So let's say in case of sessions, you would say, if nobody touches this session for 20 minutes, expire this, because this session times out, right? So this is like timing out in that way. So sliding expiration serves a totally different purpose. It has nothing to do with keeping data fresh from the cache or in comparison to the database. It is more to do with cleanup, because nobody's using that data anymore, so might as well clean up. Instead of the application keeping track of it and having to go and delete that data, the cache will take care of it. But the absolute expiration is the one that keeps the cache fresh. But absolute expiration is only an educated guess, and sometimes not even very educated, actually, because your application is going to have tens of different types of objects. You have to make a guess. Well, how long is it safe to keep this? How long is it safe to keep this? So for each of these, you're making a guess. What is the guess that you're making? That in this time, nobody else is going to update that data in the database. What if you're wrong? It's only a guess, right? In some cases, that guess is sufficient, because if your application is the only piece that is updating it, it's okay. But if there are other applications or other scripts or other entities, other people, whatever, updating the data, then you cannot rely on expirations. And that's where the next feature, which is the synchronization of cache with the database, which is something that only NCache has at this time, it becomes really, really important. Why is it important? Because it works on an event-driven model. NCache becomes a client of your database. So let's say you go ahead and specify this. I'll show you how this works. Let's say that in SQL dependency, you're saying, let's say you're adding an object to the cache. There's a corresponding row in a database table somewhere. So you're telling NCache, this object is related to this row in this table in the database. Please synchronize them. Make sure that if this row changes, the cache is also updated. So how do you do it? Again, the same way you connect with the cache. And I will go ahead and go to the definition. And when I do cache.add, I have the key, and now instead of having an object, I have a cache item which has this SQL cache dependency object. So NCache uses this feature of ADO.NET called SQL cache dependency, although this class is NCache's own, which actually you can specify a SQL statement, which in this case is going to map only to one row. NCache uses this against SQL Server. NCache now is the client of SQL. So let's say you were sitting here, you made this call here, you talk to the cache server. The cache server now talks to the database. It tells the database, I am interested in this data set. Please notify me if this data set changes. So SQL Server will send a database notification to NCache when that data set changes. And NCache will do what? It will immediately remove that item from the cache at the minimum. And by doing that, by removing that, it makes sure that you don't have a stale copy. Because next time your application wants that data, it will not find it in the cache, so it'll have to load it from the database. That's one way. I'll talk about another way. But so NCache can do this with SQL Server with Oracle, based on database events. So suddenly now NCache has become much more aware of your data source. And if you have other databases, you can use polling-based mechanism, which is another feature of NCache. You can also write CLR procedures where from within CLR procedures you make NCache calls. So let's say you're saying that if the data changes, let's have an update trigger that will call my CLR procedure, and the CLR procedure will construct a .NET object and update the cache. It'll make a cache.insert call. And of course, you should make an insert async call, because that call is being made from within a database transaction. which can time out very quickly. So it's better to make an async call. So there are different ways that you can make sure that the cache stays synchronized. But this is a very, very important feature that ensures that you can cache pretty much every data. Any questions?
So when would you recommend using the CLR store procedure versus the SQL dependency?
Good question. CLR procedures, so SQL dependency works only for updates and deletes. So if you have added data to the cache and you want to just make sure that that data is always the same version as the database, you can use the SQL dependency. The SQL dependency also has the benefit of SQL dependency is that it's not slowing down your database transactions, because a CLR procedure is being called from within the database transaction, which then calls NCache. So at least there's one network call involved in this. But CLR procedure has the benefit that it is a lot more scalable, because in case of a SQL dependency, SQL Server actually creates a data structure for every SQL dependency, because you're asking SQL Server to monitor this data, this row, right? So how is SQL Server going to monitor? It has to create some sort of a monitoring data structure. And if you had 1 million of these, SQL Server is going to choke. Or if you had hundreds of thousands of these, SQL Server is going to choke. So SQL dependency is good if you don't have hundreds of thousands of these. If you have thousands or tens of thousands. CLR procedure does not have any of those limitations, but its limitation is more on the transaction side. That it is being called from within the database transaction.
So when you say like a number of these for the SQL dependency, you mean like the SQL dependency has to create those indices on the fields, right? So you are saying if there are too many of those SQL dependencies defined on the same objects, basically this is when it's going to blow up? Or?
Actually, SQL dependency is within SQL Server. There's a broker service that gets that you have to start something, and then every time you call a SQL cache dependency, SQL Server creates a data structure where it's monitoring that SQL statement that you specified. That SQL statement could be one row, it could be multiple rows. It does not have to be a single row. Whatever you specified as a SQL statement, that becomes one data set. Then another one is another data set. So the more data sets you create, the more you're consuming resources of SQL Server.
Right. And if you are going to want to use the database synchronization for large transactional tables, millions of rows, which one would you recommend? The SQL dependency or the CLR?
So I think CLR procedures are on the more high end, but they have the drawback of being, so there's a performance impact on the transactions. So your database transactions might start to time out. But SQL dependency is not on the high end. So as I said, if you have thousands or tens of thousands go with SQL dependency, it has no impact on the database transactions. But if you have a lot of rows to synchronize, then DB dependency, that polling based, is actually more efficient than SQL dependency, but it's not as real time, because that will synchronize on a poll. So a poll happens every 15 seconds. So if you can wait 15 seconds to synchronize the next batch, then it's okay to use a DB dependency. If you cannot wait 15 seconds, go with SQL dependency. If you have hundreds of thousands of these, go with CLR procedure. Or you can go with CLR procedure to begin with if it has no impact on your database transaction. Did I answer your question? Okay. So the same way you can synchronize the cache with non-relational data sources. There's a feature called custom dependency, which is your code that runs on the cache server, and it's called on a interval. It can go and, let's say, it could make a web method call, and it can monitor a custom data source, and then based on that, you can synchronize. So these features are very important to make sure your cache is fresh. That's the most important thing for using a distributed cache. The second thing that you should be aware of is this feature called read-through, write-through. So read-through is your code that lives on the cache server. What is a read-through? A read-through is your code, so it looks like this. In case of NCache, it looks like this. So there's a read-through interface that you implement. Again, the same way you reference NCache assemblies and you use this proper namespaces. And then you implement this read-through interface right here. And it has three methods. There's an init method, which gets called at the time of cache startup. There's a dispose method, which of course when you're stopping the cache. And there's a load method, load from source. It gives you a key, and based on this key, you're supposed to figure out how to go and get your data from your database. And you provide that data back along with some other metadata like expirations and other things back to the cache. Read-through allows your cache to go and read the data from your database. So why do you need read-through? For example, let's say you do a cache.get here. What if this item is not in the cache? If there's no read-through, cache will come back with empty. But if there's read-through, cache can call the read-through. Read-through will go and get that item from the database, put it in the cache, and give it back to you also. So it's like the cache always has the data, because when it doesn't, it gets it from the database. That's one benefit of read-through. The second benefit is that you are also sort of moving your persistence layer into the cache and making your application simpler. Because the more code you have in the read-through, the less each application has to make database calls. The application just does a cache.get. So this is a really, really powerful way of centralizing your common domain object persistence at the caching layer. It's still your code. And the third benefit of read-through is that you can, at the time of expirations or database synchronization, instead of removing that item from the cache, you reload it. So you just configure this and say, when an item expires and I have a read-through implemented, just call the read-through. Why reload? I mean, why remove it? Because it's going to be reloaded anyway by the applications. And in really high transaction, let's say e-commerce type applications, you may have a lot of lookup data, which as soon as it expires, thousands of new requests will come for the same data. They'll all go to the database unnecessarily. And if this thing keeps happening over and over again, the database will have a lot of unnecessary load that it does not need to by having a reload mechanism. Reload mechanism means that the item is never removed. You have the old copy up to a certain point, and then the new copy is updated. So it really, really simplifies. So read-through is a really powerful mechanism for these two benefits. One, you centralize the persistence, and then you do a cache.get, and cache always has the data. Second, you reload data on expiration and database synchronization. Any questions on this? Now, read-through is your code that actually runs on the caching tier. So you need if the cache is a service, it's a black box. You don't have access to any of the cache servers. None of the server-side code can exist in the cache. So you don't have the ability to have read-through, write-through, cache loader, custom dependency that I talked about. None of that is possible unless you have control over the VMs where the cache is running. That is the reason why even in Azure, NCache is available in the marketplace not as a cache service. We've intentionally made it as a VM. So you just purchase the VM, pre-configured VM from the marketplace, and that gives you all this control so that you can do all these things that we just talked about. Write-through, it works just like read-through. Let me show it to it's the same way. It has a write-through interface, init, dispose, and instead of load, it now has a write method. So it gives you, now a write could be either add, update, or delete. So all three are called writes. So this has the operation type in it in terms of what type of operation it is, and then you can go and perform the actual operation. Write-through gives you the same benefit as read-through for centralizing persistence layer, but write-through has another benefit called write-behind. Write-behind is where you can just tell the cache so you can do a cache dot, let's say cache dot insert, and you can say use write behind. So cache portion of it gets updated synchronously. So you're waiting until the cache is successfully updated, but the database portion of it, you're not waiting. And when you're not waiting for the database portion, your application performance suddenly shoots up quite a bit. Just like the benefit that you're getting from reads going to the cache, now the writes are also going to the cache. Not all of them will go to the cache, but those that do, you will be able to do the writes much faster. And of course, they will eventually go to the database. And write behind is a queue that is performed asynchronously. In case of NCache, that queue is replicated on multiple servers. So if any one server goes down, the queue is not lost. Okay.
Question on the write now. How are you confirming that the write operation didn't get lost post your transaction for the
So if you do a write through or write behind and the operation fails, so it's in case of a write behind, it can even do a read try if you specify the read try, but you can have a callback which will be called, and then you will be notified that this operation failed, and then you can take a corrective action at that time. You can maybe attempt it again. You can do a more write through instead of write behind. So once your cache is fresh, it allows you to cache all sorts of data. Read through, write through gives you a lot of control. Now you're caching a lot of data. So when you cache a lot of data, the cache is starting to look a lot like a database. A lot of your application data is not in the cache. So when that is the case, just having a key-based access is not enough. Just like you're used to doing SQL searches on a database, you should be able to do the same here. In databases, you can do joins. In cache, you cannot do joins, but to counter that or to augment that, there are other features like group, subgroup, tags, which allows you to logically group multiple objects into, and then you can fetch them in one call and say, give me everybody that has this tag in it, or everybody who's part of this group. So let's say that way you don't have to do joins to collect multiple types of data. So having a SQL, let me just having a SQL search capability, for example, to do something like select something where this and issue that, do an execute reader, and just enumerate over the collection that you get back. It looks just like a database. The only thing that you have to keep in mind that when you issue a SQL query on a cache, whatever data you're searching, the entire data set has to be in the cache. You cannot do a SQL search. I mean, you can. It's going to give you wrong data. So if some of the data is in the database, some of it is in the cache, and if you issue a SQL query onto the cache will only search whatever's in the cache. It's not going to search the database. So that's the limitation, but that's where a lot of the lookup data, a lot of the reference data, you can just put it in the cache, and it's just a lot faster. Any questions?
How does it handle object relations?
As I said, there are no joins, but so everything else, what happens is when you're storing the data, you actually create indices. In case of NCache, so when you store the data, let's say you store a customer object, and you wanted to search on the customer.city attribute. So it will index city attribute. So at the time of adding a new customer object, it will extract the value of the city attribute and send that as part of the as metadata along with the actual object, which is sent as a byte stream. And then when it gets cached, the city attribute is indexed. So then you can search on the city attribute and get back all the customers that match that criteria. Did that answer your question?
Suppose you have like huge object graph.
Right.
How does it handle that?
I did not cover that aspect, but there are other things that you have to take care of. For example, what to do about collections. You can keep the entire collection as one object, or you can break it up into individual objects and store them all separately, and then you need to be able to rebuild the collection. And the same thing goes with one-to-many. You've got a customer object, you want to get all of its orders. Or you have an order object, you get all of the order items. So the same thing happens in the cache. So you can either choose to cache them all as one object. That depends on your use case. If your use case is, I'm just going to cache it for the next 5 minutes, and I know that I'm the only one who's going to use this, then you can cache it all as one object. But if you think that multiple users are going to use that and they may touch different objects, then you cache every object separately. And then you need these features like tags and groups to reconstruct them into one collection. The graph will work the same way. You can either combine the entire graph into one object and cache it, or you can break it up into multiple calls. And then you have to get the first object, get its subnodes, and get each, so make multiple calls to the cache. The same way that you do with the database. But again, it depends on your use case. And I didn't go into that because then I didn't have enough time to cover. But there's a whole topic of how do you handle relationships. I only had this one small line, and I intentionally just skipped it because as soon as I start talking about it, then it becomes a whole topic of its own, and then I can't cover the other topics. But that's something that in case of NCache, you can definitely do it through cache dependency, and cache will ensure that those relationships are honored in terms of automatically removing objects. If one object is removed, the other one is automatically removed. But you still have to figure out whether you want to cache them all as one object or break them up. That's your personal. I'm going to, how much time do we have, Andy? Okay, so let me just speed up. Quickly, runtime, we've gone over, so there's key-based events, there's cache-level events, there's custom pub-sub type of events, there's continuous query. A continuous query is also a feature that only NCache has on the .NET side. Java side caches have it, but on the .NET side, only NCache has it. I'm not going to go into the detail of this because then I won't be able to cover the other part. So one of the things that people don't realize is, let's say if you were using an in-proc standalone cache, let's say ASP.NET Cache object, is that in an in-proc cache, all the data is kept in an object form within your process's heap. So the access is super fast. As soon as you go into an out-of-process cache, objects have to be serialized. They have to be transported across the network. Let's say from you do a cache.get or cache.add here, the object gets serialized, sent here. So many customers call us and say, we are looking at NCache to speed up our things, and our application performance actually slowed down. We were using ASP.NET Cache object, and there everything was hunky-dory. It was super fast. We had limitations, of course. We couldn't scale. We couldn't go beyond one process and all the other stuff. But it was fast. So then, we say, well, first of all, you have to accept this, that a distributed cache, the data has to be serialized. Serialization is one of the biggest costs in this entire activity, and then it has to be shipped. But there's a way that we can counter this. NCache has this feature called client cache. Most of the Java caches have this. They call it near cache. Redis does not have this feature, by the way. And this is a feature where you actually keep a subset of this within the application process, within your application process in an object form. It's like a standalone in-proc cache. The only difference is this cache knows that it is part of an overall distributed cache infrastructure. So it stays synchronized. What that means is it registers itself with the caching tier. In case of NCache, NCache has a mechanism where a client cache can register itself. So every data that gets put into the client cache, that gets registered to the corresponding object in the caching tier. And if another client goes and updates that item, the caching tier notifies that client cache. So the client cache can go and update itself. So it's an eventual consistency model. Eventual is pretty fast. I mean, we're talking milliseconds. We're not talking minutes. But it's still, so the cache gets updated first, and then the client cache gets updated in an asynchronous fashion. By having the client cache, you suddenly get all the benefits of that standalone in-proc cache without all the limitations of a standalone in-proc cache. The limitations of standalone in-proc cache is it's one process only. It cannot grow beyond a certain time, beyond a certain size. It cannot replicate. It cannot go across multiple servers. It cannot even go on multiple processes on the same box. So all the limitations are there, but the benefit is it's super fast. Now you get none of the limitations, but the benefits of super fast are provided through this client cache or near cache feature. So if you use a distributed cache, make sure that you use this feature. And this is an application data caching feature. You don't use this with sessions. You do this when you do more reads than writes. Because in case of a write, you're updating two places. You're updating the client cache, and then you're updating the caching tier, or let's say both places. So the updates are actually slower. But if the updates are not as many as reads, then the reads are super fast. In case of sessions, there's one read and one write always. So there are equal number of reads and writes. So the benefit is not there in case of sessions. In case of view state, the benefit is not there. But in case of application data caching, there's a lot of benefit. So you should configure this. In case of NCache, it's really easy because you just configure it through the configuration. There's no extra programming that you have to do. You just program as if you're talking to the caching tier. That same cache.get, everything is the same, just plugs in behind the scenes and starts to cache stuff on the client end. So this is a really powerful feature that I wanted you to know about. Another thing, a distributed cache is just like your database. It runs in your production, in your data center, and just like you cannot afford for your database to go down because your application will stop working, you cannot afford for the cache to go down. So if a distributed cache does not give you truly high availability, just because you can add more servers doesn't mean it's high available. So for example, if you drop a node, in case of NCache, so first of all, peer-to-peer architecture is something where every node in the cluster is equal. So there's no master slave, there's no majority rule concept. That means you can truly add or remove any server and the cache will continue to work. Second, you can change configuration at runtime. In case of NCache, for example, I showed you that list on the client side of list of servers. What if you add another server at runtime? If you started with 2, now add a third one, how would the clients know? You can't restart a client because restarting a client is disruption. So in case of NCache, you don't have to, because NCache will automatically update what we call the cluster membership map. This doesn't show here. And then that gets propagated to all the clients. The clients now have a new cluster membership. It has a third server, so they can connect to it as well. Similarly, there's in case of partitioning, there's a distribution map that contains the bucket list, which buckets are in which partition. That gets also propagated, and that bucket map changes only when you add or remove servers. So for example, let's say you started with a 2-node cache cluster. Everything is fine. You just added a third one because this was a maximum capacity. So you added a third one. This has to happen at runtime. So adding a third server means that a third partition is created at runtime. And that means some of the data from partition 1 and partition 2 is automatically shifted to partition 3, all at runtime without any, and the application is working. There's no stoppage, nothing. And partition 3 now has to have a replica created here where it used to be replica 2, now there's replica 3, and replica 2 is now created on this cache, new cache server. So all this shifting of data is done automatically, has to be done automatically. If it is not done automatically, then cache is not highly available. None of the other caches support this on the .NET side. You can do it, you have to do it manually, you have to do manual intervention. Here it's all done automatically. Similarly, what if this server goes down? Should the cache stop? No. So partition 3 is lost. Well, there's a replica that used to be passive, now it becomes active. And now that it became active, it realizes, well, there are only 2 servers and 3 partitions. So I got to merge myself into partition 1 and 2, and I need to go away, basically. So it merges itself in these 2 partitions, and then a replica for partition 2 is created here. So you can go back or forward without any stoppage. So any distributed cache that does not give you this as an architecture will make your application. We have customers that will not even upgrade they will wait many months before they have a scheduled downtime to upgrade. Sometimes they don't. And many of our customers are they want to do a live upgrade, where they don't want to stop even when they're doing the upgrade of the cache, let alone just a normal operation. So any customer of ours that almost all of our customers have requirement that the application has to be highly available, just like you would do with your database. So if you have a high, and again, high availability becomes more sensitive. Why? Because you have so many people using your application now. Scalability means what? Lots of people, a lot of activity. Either it's lots of people, it's lots of business transactions. Either way, the cost of downtime is very, very high. So make sure that your cache handles this. In case of NCache, it also does WAN replication, which is something that you don't have in Redis. On the Java side you do, but not. What I'm trying to do is make you guys see that this is not an NCache specific feature. The Java industry is fairly mature in this space, and most of them have these features that NCache has. But on the .NET side, NCache is the only one. So if you have multiple data centers, which is becoming more and more common now, you expect your database to replicate. Why not the cache? What are you going to do if the cache doesn't replicate? How are you going to do DR? What's going to happen to your sessions? Even if you can reload the application data, what's going to happen to the sessions or any other transient data? So this is really important. Okay, NCache is the oldest cache in this space. We are pretty much, in fact, AON is also our customer, but here's just a last slide, a comparison of NCache with Redis. They're both open source. The Windows version of Redis that is open source was ported by Microsoft OpenTech, but ironically, Microsoft doesn't use that version in Azure. The version that they use is the Linux version. That's the Redis Labs version. So, and because it's a cache as a service, you don't see it, because it's a black box. So if you're planning to use the Windows version, you should know. A lot of customers complain about this. NCache, of course, is both open source and there's an enterprise edition. We are on-prem, we're in Azure, we're in Amazon. And I already mentioned Redis has a cache as a service model. We have a cache as a server, as a VM model. And that allows you to have the read-through, write-through, custom dependency. There's also other features that I didn't even go into. And of course, it gives you total control, so you know how many servers you have, what is the consumption of CPU and everything. It's like I was talking to you in Azure SQL database and SQL Server. All the serious database players use SQL Server. SQL database is a lot of convenience, of course, but it's for the more of an SME use. The same thing with cache. The cache as a service is more for the lower end of the use. If you're a serious player, then you want to control your cache. That's the end of my talk. Any questions?
Cluster interaction with clouds. You can cluster shrink or span of values depending on the load.
In terms of, I didn't understand your question.
Can cluster shrink or expand?
You mean the cost?
Yeah.
Cost?
Minimize the cost of the running cache in cloud.
Actually, so in case of NCache, the cost is the same whether you're in the cloud or in the on-prem. So there's an open source version which is totally free. There's no limitation built into it other than some features. So there's no limitation of size or anything.
Suppose I have like a peak of the activity. Can the cluster respond to that by adding the nodes automatically?
You can configure it through scripting, yes, but again, we want you to control that. We want you to determine, because you need to also have more resources available to add. What if your subscription did not allow? So there are a lot of other things. So it cannot be automatic, but you can add in a very seamless fashion at runtime as your capacity starts to grow. And the same way you can drop.
You could essentially script to spin up a VM from the template of the NCache server and then replicate your cache on it. And
Yes, yes. Guys, we're going to quickly do a draw. So thank you very much for your patience.
Has anyone not filled out this who wants to participate?
Please put your name on the sheets so that you are part of the draw.